This one. This one. And this one. Oh, that was last week's lab. Nobody was here last week, so we didn't do the lab in the lab. So you have to go online. Do you have a copy of the Ka with acetic acid?
Acetic acid?
Yeah. This one?
Yeah, I'm sure you have copies online. Sure.
Yeah, I got a hard copy here.
Okay.
You'll have to go into the
Videos and
yeah, and watch the video demonstration to get the lab. Okay, and these are the documents. Let me show Elizabeth. That's chapter 16 that we're on now.
Okay.
And then this is the review document.
Okay.
That's version 2. I got 2 versions because I had too many problems in there, if you can believe that, in my first iteration. So I split them into 2, and the version 2 tended to be better attuned to what we were covering, and they're the review problem, work problems. We'll need 2 of those. And that's the version that we'll use next week for review. If I didn't mention it before, whatever you learn in the equilibrium chapters, don't forget that, because we're going to revisit equilibrium several times. We've already done that for acids and bases, equilibrium. Now we're going to look at solubility issues as equilibrium problems. And then, once we get that in hand, we're going to look at complex ions, which are kind of an odd form of equilibrium, but still the concepts hold true for both of these, actually. So let's see what's unique about solubility. Remember when I was talking about equilibrium in the beginning, we started off with just K as our equilibrium constant. And I mentioned that we could use subscripts to indicate what type of solubility constant this was. Excuse me, what type of equilibrium constant this was. This one is subscript SP, stands for solubility product. And the reason for that is based upon, I'll just use the generic first. If you have a binary compound that is a solid, and you try to put it in an aqueous solution, well, we've talked about solubility in terms of yes and no, no in-betweens. That was in 101, I think. But most solids, salts, and that's primarily what we're discussing here. Most salts may be on the bulk insoluble, but they do have a very limited solubility, and we can quantify that. So this can become in an aqueous solution, and that in aqueous solution. Okay? So even though we say it's insoluble, there's a little bit of that goes into solution. Maybe not much, maybe a very small amount, but it's significant for equilibrium discussions. And then this KSP would just be, well, the way this is written, it would just be, let me do it wrong first, and then I'll show you the right way. We would generally write this one times this one, right, divided by this one, right? Except that's a solid, so it doesn't count. right? And that's the case for all solubility products. The solid is on the left, the dissolved ions are on the right. So when you cross that out, you get nothing left but this times that. And mathematically speaking, that's a product, as opposed to a quotient, which would be one divided by the other. This is a product. So that's why we call it the solubility product, because it's always the ions multiplied by each other in an equilibrium fashion. So if you have coefficients here, then they become powers. As always, there's no difference there with these equilibrium expressions. In this example is bismuth sulfide, and it goes into solution to produce 2 bismuth 3+ ions and 3 sulfur sulfide 2- ions. So its expression would be bismuth to the 2nd power and sulfide to the 3rd power. Now that's the solubility product expression. It's like an equilibrium expression. And as long as the temperature stays the same, it doesn't matter what the concentrations are. Right? The product will always be the same, just like equilibrium. As opposed to equilibrium position. Remember that distinction between equilibrium constant and equilibrium position. The equilibrium position can be wildly different, but the expression will always give you the same K if the temperature stays the same. So in this case, what we're saying is the equilibrium position is in terms of solubility. How much of that will actually go into solution? And we usually, it could be mass per unit volume, but we're going to primarily stick with molarity. How many moles of this will go into solution in 1 liter? And we generally give it a value of S for solubility. And it's in terms of moles of this. So if you have multiples over here, then this one, if this is, let's be consistent, well, let's just use what's on the board. If you've got 2 bismuth and 3 sulfides, if you have 1 mole of bismuth sulfide go into solution, 1 mole per liter, then what does that mean for ions? That means the bismuth ion is 2 moles per liter, and the sulfide ion is 3 moles per liter. So if you make the individual concentrations proportional to this, then you will have to introduce the coefficients in your ICE table. We're going to use ICE tables, at least in the beginning, just to get a feel for it. And the solubility expressions are very predictable. So you may get to the point where you don't need an ICE table. But in the beginning, we'll use the ICE table because it tends to give us a better segue from equilibrium into solubility. Boy, that was stuck up there. All right. And this is just a check, see if what I just said registers. If we compare several salts at a given temperature, right, same temperature, does a higher KSP value always mean a higher solubility? Right, think of that in terms of equilibrium versus position. Right? Remember, position was not always the same for the KSPs. Right? And the same logic operates here with KSP versus solubility. Right? Solubility is an expression of mass or moles per unit volume. That's all it is. It says nothing about equilibrium. Well, it says nothing directly about equilibrium. We're going to learn how to use solubility to determine equilibrium constants, the solubility product. But in and of itself, it doesn't say anything about equilibrium. And for another reason, KSP incorporates those coefficients as powers. So the solubility might be one value, and once you get through introducing powers, the KSP can be just wildly different. For instance, if we say sodium chloride, right? We're going to take sodium chloride, and believe it or not, sodium chloride has a limit of solubility. So we can make this expression valid, right? There you go. And these are aqueous. We're going to stick with aqueous from now on. Then if we say solubility is an expression of how much of this goes into solution, then when it goes into solution, how much of that does it produce? Right? If some of this goes into solution, let's use the ice table. Then we start off at, well, nothing here because that's solid. It doesn't have a term. But we end up over here with starting off with 0, and then we end up with equal amounts from the solubility of that one. Right? So we got plus S and a plus S. Right? So if 1 mole of this goes into solution, 1 mole of that, and 1 mole of that are both in solution. So that means our equilibrium expression has this and this as in its terms. And that means the KSP is equal to S times S, which is S squared. Okay? That's a simple one. Let's try more complex one. I think my example is sodium phosphate. So we got sodium again, but this time it's bound with phosphate. Okay? How does this go into solution? Well, you produce 3 sodium ions and 1 phosphate. And of course, they're aqueous. Now, the solubility here is that expression, so many moles per liter. And what does that mean for sodium? Well, we start off with 0, but we end up with what? 3 moles for every one of these. So this would be 3S. If one of these goes into solution, 3 of those are ionic. Okay? And 1 of these. So that means we have 3S and S, and our KSP expression is this times that. Well, actually, it's like this. And then this one is to the power of 3. So what does that give us? Well, the S's are, add your exponent, your exponents. 3 plus 1 is 4. So it'd be S to the 4th power. And then this 3 to the 3rd power, which is 3 times 3 is 9, 3 times 9, 27. Okay? So you can have the exact same solubility. I'm not saying that it is, but if you had the same solubility for sodium chloride and sodium phosphate, you would have a completely different KSP because of these factors. And it's based upon how many ions are produced by the salt that goes into solution. Okay. That's the whole point of this discussion, is that solubility product and solubility are not the same animal. Although we did use solubility to give us the KSP. Okay. But the expression is not the same. So let's move on. So here we have, we're going to work backwards now. Here we work toward the solubility. Now we're going to take the solubility product. We work toward the solubility product. Now we're going to work backwards from the solubility product to the solubility. Okay, so silver chloride. And if you look on that chart that, well, I gave you in 101, you'll find that silver and chloride together are considered insoluble. But there's insoluble and then there's insoluble. In other words, the solubility of silver chloride is very, very, very low, but it's still a positive value. 1.6 times 10 to the minus 10 is the solubility product. So let's see what that means. Silver chloride solid will produce silver ions and chloride ions. Okay? And KSP is 1.6 times 10 to the minus 10. Now, what does that mean? That means silver times chloride, right? Because we have a coefficient of 1 and 1. So that's it. That's all of them. Okay? Come on. There we go. So, PowerPoint is messing with me. They took my double barbed arrow and turned it into a square. Okay, so anytime you see a square on these slides today, that's a double barbed arrow. Okay, so we've got that expression for solubility of silver chloride. And here's our expression for the KSP. Now, what does that mean in terms of, we'll go back to the ice table just so we can get our bearings. Right? We start off with nothing here, and then so much of this goes into solution. That means plus S and plus S, right? S and S, 1 to 1, 1, 1. That's the ratio. That means we have S here and S here. That means this is S and this is S, which equals S squared. So S equals the square root of 1.6 times 10 to the minus 10. Okay? And that's 1.3 times 10 to the minus 5 molar. Right? That's how we got the solubility out of this. Based on this value, we work back through our ice table. And you'll see a pattern emerges. When you have two ions produced from the solid, it's always solubility product equals S squared. How about silver phosphate? Let's try that one. If you look in your solubility chart, it'll say, oh, that one's insoluble too. But it's only, well now, this doesn't say the solubility is less than silver chloride. This says the KSP is less than silver chloride. The only way we know whether the solubility is less than silver chloride is to do the calculations. Right? We've got 1.3 times 10 to the minus 5 molar for silver chloride at a given temperature. At the same temperature, silver phosphate produces, because this one's 3 minus, and that one's 1 plus, so we have to have 3 silvers. And then we have a phosphate over here. All right, so now what do we get? Well, if one of these goes into solution, it produces 3 of those. And it produces 1 of these. Correct? Okay. So that means we have 3S and S. I can see where this one's going. We already did one with sodium phosphate. It's going to give us the same result. for the S's. But the calculation will give us a different value, of course. All right, so if KSP is 1.8 times 10 to the minus 18, then that's equal to this one, 3S, equilibrium concentration, to the third power, times this one to the first power. Okay? So this one is, we found it earlier, it was 27 S to the fourth power. So we need to divide both sides by 27 and then take the fourth root of that number. Let's just do that one for kicks. Since we're just getting started, so 27 divided into this number, 1.8 in an exponent minus 18, divided by 27, and that's 6.67 times 10 to the minus 20 equals S to the fourth. So S is equal to the fourth root of this number. Let's see if I can do that one. Oh, this calculator doesn't have one of those roots. Okay, so I have to improvise. So I'm going to take this number to the negative fourth power. Remember that from math? Fourth root is like the negative power of that. So let me see. I've got this number in here, and I'm going to say negative fourth power. Hit my power key. Is that right? Let me see what they got. No, that's wrong. Oh, that's not right. I should have known better. Let me put it back in here. Oh, that's not it either. Hold on a second. 6.67 exponent 20 negative power. It's not the negative fourth power, it's 1/4 power. Okay? I didn't mean to confuse you. I was confusing myself. So if I take the negative fourth power of that, so let's see, 0.25 and then hit the power key. There it is, 1.6 times 10 to the minus 5. There you go. So, as it turns out, silver phosphate is more soluble than silver chloride. Right? We could not compare the KSPs because the salts produce different numbers of ions. And when they do that, they give you this form of equality to the KSP. Now, if you're comparing salts that all produce the same number of ions, then you should be able to compare the KSPs and deduce which is more soluble. But if they produce different numbers of ions, you have to actually calculate solubility. And it turns out silver phosphate is more soluble than silver chloride, even though these values are radically different. This one's a lot smaller. Okay? That was my point for this whole discussion. All right. Now, that was in trying to dissolve a salt in pure water. Now we're going to look at the effect of an acidic solution on the solubility. Right? Now we think back to our equilibrium discussion where we were talking about common ion effect. Is there a common ion when you acidify the solution with nitric acid? Right? So if we say silver chloride, again, yield silver and chloride ions. And what would affect their solubility, right? Think Le Chatelier. If we introduce either one of these, it will drive the reaction back to solid and reduce the solubility. But do we have any common ions when we put this one in solution? No. This will have no effect on the solubility of silver chloride. There are no common ions here to interact with it. And that's the short version, right? If you add those two equations together, you get no impact on the solubility of this because there are no common ions. Okay? Now, what if we do put a common ion in? Let's change it to hydrochloric acid. You can acidify it to the same pH with either acid, right? We can do that. But in this case, you're introducing chloride ions into that environment, and you're driving the solubility backwards. So the solubility in this acidic solution with hydrochloric acid is much, much less. Now, where would that become a practical application? Well, suppose you were trying to extract all the silver chloride from a solution. Right? You know it's very limited solubility, but you want to get all of it out of there. So what do? You acidify the hell out of that solution with hydrochloric acid. And that drives virtually all of the silver out of solution, or at least a lot more than you had before. Okay. Okay, this is a different example. Right? Similar concepts, but different example. We're going to look at silver phosphate for this one. And I don't have to draw that on the board because it's right here on the screen. Solubility of silver phosphate in water compared to silver phosphate in acidic solution. If you make it nitric acid, again, now we have a different salt. So look at the combination. This is the expression with a double barbed arrow there. Use your imagination. Silver phosphate produces 3 silvers and 1 phosphate ion in solution. Now we're going to introduce nitric acid. Okay, what do we get? We get this combination, right? So there's our silver phosphate, there's our nitric acid, there's this one. This is going to produce, is going to go completely to hydrogens and to protons and nitrates. Right? So we probably even shouldn't even put that one there because there's none of this left. It's all gone. It's over here. So what happens? Well, look at phosphoric acid. What does phosphoric acid do in solution? Well, it has to go through several deprotonations to get the phosphate. Remember, the equilibrium constant for phosphate is based upon HPO2 minus, HPO42 minus, yielding PO43 minus, and has a very, very, very low equilibrium constant. So where does it want to do? This one would rather be that one. And in fact, that one would rather be, well, it didn't say, but that one would rather be H2PO4 minus, and that one would rather be H3PO4 3 minus. So what you're doing is you're taking this one and you're removing this hydrogen to make that, right? Which drives the reaction this way. Right? It's increasing the solubility of silver phosphate because we're removing that ion. Right? So that ion which is a strong base. Right? It comes from a weak acid, so it's a very strong base. And it removes this hydrogen and produces that one. So it drives the reaction this direction. Okay? And that makes silver phosphate more soluble. Okay, now that was the qualitative description of what would happen if we acidify with nitric acid a solution in equilibrium with its solid of silver phosphate in aqueous solution. So we've acidified it and we've made it more soluble, but how much more soluble? Well, first of all, did the KSPs change for silver phosphate? No. KSP is still the same because we didn't change the temperature. The equilibrium position changed. The solubility changed, but not the KSP. Oh, okay. I thought we were going to do actually calculate how soluble it is, but we can't do that unless we know how much nitric acid is in solution. That's required. And we'll do one of those, that type of reaction in just a second. In this case, we're going to look at the solubility of silver chloride. There's its KSP again. Only this time, we're going to use 100 milliliters of 4 times 10 to the minus third molar calcium chloride in solution. Chloride is a common ion. So this is going to have an impact on the solubility of silver chloride. But which direction is it going to go? Right? If it produces silver ions, that's chloride ions. We add chloride ions here. It's going to increase this and drive the reaction backwards, which decreases its solubility. So here's our ice table. When you're doing this type of problem, ice table is a good idea because you're introducing a coupled reaction. Right, so we've got initial conditions, change, equilibrium. All right, so silver, this doesn't count, but just recognize that we're still interested in the solubility of that solid. So what are we starting off with? Well, if we start off at 0 here, but we've also introduced some chloride ions. And notice that when calcium chloride goes into solution, it produces 1 calcium, but 2 chlorides. So if the concentration is 4 times 10 to the minus third, then the concentration of chloride is actually 8 times 10 to the minus third. Well, let's not throw away any significant figures here. Okay, and these are all molarity. Okay, so now we start off with 0 silver, so we're going to get some of this in solution, right? It's going to go. So in this case, we don't have that over here. Well, actually, we do. If one of these goes into solution, you get one of those. So that's true. We do get one of these. I've got it as X here, same concept. And one of those and one of these goes into solution. Okay. So now we get S and S plus 8 times 10 to the minus third. So these are our equilibrium terms that go into the expression of KSP equals 1.6 times 10 to the minus 10. That's equal to S Equilibrium, let's be consistent here. S. And then S plus 8.00 times 10 to the minus third. Okay. All right. So what if, in this case, we say that so little S is going into solution that this term can be ignored? Let's just see what happens. That means it would be this term times that one, or 8 times 10 to the minus 3 S. And then we solve for S. And to save myself the trouble, 2 times 10 to the minus 8. Now that's what we think it is based upon that approximation. Let's see, am I going to do a 5% rule here? Oh, this comment is valid. 100 milliliters doesn't matter because the concentration is given already. Right, so that's a little blue smoke there. No. Okay, we're assuming that it meets the 5% rule. So how do we judge the 5% rule? Well, you would take this value and plug it in here and see, is it within 5% of that value? I'm interested to do that. Let me just see how close it is. So we're going to take this value here, and we'll plug it back in here and here, and calculate this value. So let's see, 2 times 10 to the minus 8 plus 8 times 10 to the minus 3. And then put that value in here, 2 exponent 8 minus, and multiply those two together. Okay, what did I do wrong? Did the right number, 2 times 10 minus 8. 2 times 10 minus 8 times, right. No, excuse me. Okay, I multiplied the wrong values, excuse me. This is so small. I mean, I verified it in my calculator. When you add this to this, you're going to come up with 8 times 10 to the minus 3. Then times 2 times 10 to the minus 8. There. Now times. So, okay. Not only are we're inside, we're less than 5%. We're no error whatsoever. It's exactly the same value. At least to 2 significant figures. Okay. So we're good on that value. The approximation was valid. So let's see, what are we doing now? Calculate solubility of silver chloride in 4 times 10 to the minus 3rd calcium nitrate. Oh. Calcium nitrate? Are there any common ions there? Well, we could have calcium and chloride react, but that's completely soluble, right? And nitrate and silver are completely soluble. So calcium nitrate will not affect the solubility whatsoever. We could treat this as just like that, with calcium nitrate in solution. And then this would become like this. Just take the square root of that value. What was it? 1.3 times 10 to the minus 5, I think. Yeah. So it's the same solubility as pure water. because we have no common ion to shift the equilibrium. The KSP is still the same. It's always the same, no matter what you add. Solubility may change depending on common ion. Let's see, I'm gonna leave that there for a second. Okay. It's often useful to be able to predict whether or not a precipitation will form when you mix two ions together, two solutions with that form an insoluble compound. So we have, for instance, in the past we've used, so we'll erase that one. We've used silver nitrate, which is completely soluble, and then sodium chloride, which is completely soluble, yielding what? Silver chloride, which is insoluble for all intents and purposes, and then sodium nitrate, which is soluble. Okay, that's where you add these free ions together and you get a double replacement reaction and produce silver chloride solid. Well, we want to know at what concentration of these ions will that solid form. Right? If we make this extremely dilute solution, maybe that solid won't even form. So at what point will it form? And here we go back to calculating the Q value and comparing it with the K. Right? If the Q is greater than KSP, you will get precipitation. Why? Because the Q says you have more of this than you do that. Right? If that's bigger, then you're going to get that solid. Whereas if the Q is less, that means that hold on a second. Let me say that right. If the Q, all right, so let's back up. The Q in this calculation would be the opposite of this one. Okay. See, where I made my mistake was I was talking about this reaction thinking of Q, but we're not calculating the Q for that reaction, we're calculating it for this one. So the Q, if the Q is greater than KSP, that means we got too much of this and it's going to drive the reaction back to that. Okay, so we will get precipitation. But if the Q is less than KSP, that means we don't have enough of this. And this is going to go into solution. And no precipitation. Think of it in reverse terms. So what would the KSP is, well, let's see, Q. Q is the same as always. What is the actual concentration of silver ions and chloride ions? There we go. And compare that to the KSP, which is the equilibrium concentration. If Q is greater than KSP, you get precipitation. If Q is less than KSP, you get no precipitation. So what you need to know is the actual concentration of ions in solution. So if you start off with a solution like this, then you have a concentration of silver ions and you have a concentration of chloride ions that plug into this reaction. Then you can calculate the Q. Okay. Now, since we know that each reaction of a mixture of ions will give us different K and different Q values. And we can use that information to selectively precipitate metal ions from solution. All we need is to select the right conditions where the Q of that particular metal ion and the chosen anion will exceed the KSP for that ion, for that compound. And if we do that judiciously, we can selectively precipitate out metals in sequence. We get the most insoluble first. Well, actually, it's not always that case. There are other considerations, and we'll look at those as we proceed. Here's a very simple example. We have barium and silver in the same solution. Right? We could say, just say it's nitrates, right? Barium nitrate, silver nitrate. They're both soluble, right? Remember the rules? All nitrates are soluble, period. Adding hydrochloric acid will form a precipitate of silver chloride. And barium chloride is completely soluble. So we get the silver chloride out of solution, then how do you separate them? Usually filtration is a good idea. You've got a solid suspended in a liquid, all you need is the correct filter with a small enough pore size, and you can remove the solid, and then the what's left over has your barium in it, and then you can choose the reaction to remove the barium from solution. Either precipitate it with a different anion, or just evaporate all the water if there's nothing else in there but barium. So why would we not use sodium chloride? I mean, it's got chloride ions in it. That would precipitate out. Well, you contaminate your barium with sodium then, right? If you use hydrochloric acid, then hydrogen ions just means the solution is acidic. All right, how about copper 2+, mercury 2+, nickel 2+, manganese 2+. And what happens if we add hydrogen sulfide to that solution? All right. Let's see if we can make sense of this thing. We've got those 4 ions. Let me just write them up here. Copper 2+, mercury 2+. Yep. Mercury 2+, nickel 2+, manganese plus, and we're going to use hydrogen sulfide as our first step. So at low pH, sulfide is relatively low. If we have low pH, then the sulfide ion concentration is very low. Why is that? Because in solution, hydrogen sulfide is a weak acid. So it produces this plus this, 2 of these, and that. Okay, these are in solution. Actually, this is dissolved in solution too. But we produce, and this is the ion that you need to precipitate some of these metals. Okay? But remember, the Q has to be greater than the KSP. So if we want to precipitate some of them, but not all of them, we find the ones where the KSP is going to be less than the Q. And in order to do that, we need the concentrations of this component to be very small. Right? Then you get the very insoluble ones first. And as it turns out, if you have a very low pH means lots of these. Right? Lots of those hydrogen ions. So how do we do that? Well, you need to acidify the solution somehow. Right? Let's see. Nitric acid would be best. Because all nitrates are soluble, nitrate's not going to interfere with the solubility of your metals. So if you use nitric acid and acidify this solution, then you will have it, right? You will drive the reaction back this way. Means very low concentration of sulfide. Okay. As it turns out, very low concentration of sulfide will still precipitate this one as the sulfide and this one as the sulfide, because they have extremely low solubility with sulfide. Okay. Then if you want to, okay, so here's the explanation. Overall, K for this reaction is 10 to the minus 20. So if you acidify it, you make it even a lower concentration of sulfide ions. Then what do? Then if you add hydroxyls, okay, some kind of hydroxyl, let's see, what would be a good hydroxyl? Sodium hydroxide would work because sodium sulfide is also soluble. So if you use sodium hydroxide, then you could shift this reaction back to the right and produce more sulfide ions. Now you're going to pull out the ones that have a higher solubility with sulfide. Right? So here's the decision tree. We're going to precipitate copper and mercury with an acidified solution of hydrogen sulfide, hydrosulfuric acid. Then we have left in solution is manganese and nickel. Now we're going to increase the pH to 8, and now that precipitates manganese and nickel because we have increased the concentration here. Now the Q exceeds the solubility product for these two. That's the whole logic for sequential precipitations to remove metals from solution. And this is done on an industrial scale, especially when you're trying to get at valuable metals in a mixture. Right? If you have a solubilized mixture of metals from your ore, say you've gone through the bulk precipitations where you've removed most of the copper, but there's still some copper in there that you want to get at. Then you could use this scenario to get that copper out. And then you might even still have some nickel in there. Nickel's valuable. Manganese is valuable too. So then you could remove those on an industrial scale, because acids, nitric acid and sodium hydroxide, they're dirt cheap. You can do these reactions for pennies. Okay, so this is an expanded view of a scenario for separating a very complex mixture of metals. And this comes straight out of your book, right? That's why I just left it small print. It's not going to show up very well on the video, but it's in your book. And if you have this complex mixture, right, and it's been color coded for us, right? So the first group that comes out are these right here: silver, lead 2+, and mercury 1+. And what we do here is we add hydrochloric acid. And the chloride removes silver, mercury 1, and lead 2. Those are out. Now the second group, we add hydrogen sulfide, hydrosulfuric acid. It's already acidified, so we add this, and that precipitates this group: copper, bismuth, cadmium, lead, mercury 2+, arsenic, antimony, and tin. They come out in the second precipitation. Then we add hydroxyls. We change the pH to something near 8. Now this picks up the hydroxides of aluminum, iron, chromium, zinc, nickel, cobalt, manganese, and iron 2+. And then what's left over? Well, the rest you can get out with carbonate. It's already basic, so you can get sodium carbonate into solution fairly easily. And then the carbonates, barium, calcium, and magnesium carbonate come out of solution, and all you got left in this group is ammonium in solution. Now that's the first bulk separation. Beyond that, these groups, you got to figure out how to get these separated from one another. So it can get pretty complex, but it just depends on what's the incentive. I mean, are you a researcher and you've got an unlimited grant budget that you can do this stuff? Or are you running a business? And how valuable are the metals that you're going to remove from solution? And then you can do the math as a businessman or woman and determine whether it's worth doing. Okay, that was solubility. Now we're going to look at complex ions. I've got a couple of handouts. I'm debating whether to give them to you. It's not stuff that I'm going to require you to memorize. Actually, this would be pretty valuable. This is nomenclature for coordination compounds. And I'll just give you a copy of it. You can look at it if you want. And then this one is a formation constants for the complex ions. I haven't defined formation constants yet, so hold on and we'll get there. Okay. Here's the basic concept of complex ions. They consist of a metal ion surrounded by one or more ligands. Oops, forgot to plug in my power. There we go. I got a low battery notice there. So, the metal ions serve as Lewis acids. In other words, they accept electrons. And the ligands serve as Lewis bases. They donate electrons. And they form a stable complex in solution, right? All of this is happening in solution. So the reaction goes from, say, metal in solution, just for example, and then various ligands. Let's say we're going to put 2 ligands with it. Actually, charges only have to balance. They don't have to be neutral. So let's do that. Just do it like that. This will illustrate a point. And they're in equilibrium with the complex ion in solution. So here's the metal, and here are the 2 ligands attached to it. Okay? So what's the charge on that complex ion? Well, we've got 2 minuses and 1 plus, so that ion is a -1. Okay? The charges have to balance, but they don't have to be neutral. And all of this is in solution. We can write an equilibrium expression for this thing. Let's see, complex ion formation. Case of F is the formation constant for the complex ion. And in that case, we would have this one, right, divided by this one, and this one squared. That will give us a value for that equilibrium. Some of these equilibria are way, way to the right, just like any equilibrium, and some of them are way to the left. Now, this is important also. Each step of the reaction of the addition of a ligand has its own equilibrium constant. So this is overall, right? Because we're putting two ligands on that metal. But what actually happens is one ligand goes on, and makes that. So it's got a K value. And then this one adds another ligand. And it has a K value. Okay? So this is overall, and these all go through steps one at a time. Does that remind you anything? Acids, how they deprotonate one proton at a time. If they've got two protons, they each come off in sequence. And each one has an equilibrium constant. Same concept, one ligand at a time. All right, here's an example. Where we have beryllium 2+, right? So is that valid? Beryllium. Yeah, beryllium is an alkaline earth, so it has 2+ charge. So we put that in solution with fluorides, and the first reaction adds a fluoride ligand with this coefficient, this K value. Okay, and it's way, way to the right, right? 10 to the 4th. Let's see, 10 to the 4th is 10,000, so 79,000. So it's way over here. So then this one picks up another fluoride, and it's 10 to the 3rd, so it's way to the right. This one picks up another one, right? That one comes down here, picks up another fluoride, and it's way to the right too. And this one picks up another one. And now we have beryllium with 4 fluoride ligands and a 2- charge. And its last K is 10 to the 1st power. So what's the overall K? Well, Hess's law, right? We're going to use Hess, except we're not going to talk about enthalpy. We're going to talk about K. We can add these together and get this overall reaction. And the overall K for this is 10 to the 12th, right? So when we add these reactions, what do we do with the Ks? Remember, multiply them. Multiply these Ks together, and you get 7.5 times 10 to the 12th, this overall reaction. So what is the end result of beryllium and fluoride in solution? Beryllium with 4 fluorines and a 2- charge. Okay? So it may take these individual steps, and they can be determined, but for all intents and purposes, you've got nothing but this in solution. Okay? That's the moral of that story. Okay. Suppose we have a water-insoluble ionic solid, like silver chloride. Actually, any one. There are 2 ways to get that solid into solution. You want to make it go into solution. The first way we've looked at already, common ion. And the other way is complex ions. And it depends on the response of the solid to its environment as to which one works best. Okay? So if an anion of the solid is a good base, like PO4 3-, it's a very powerful, strong base. It goes for hydrogen ions really well. If that's the case, then all we have to do is acidify the solution with the appropriate acid. And this will pick up those. Remember that? Right? This will pick up those protons. If we acidify the solution, it will pick up those protons and make and remove that phosphate from solution and make this. Actually, probably goes all the way to H3PO4. But for this reaction, that's all that matters. And it'll drive the reaction to the right. So if your anion is a strong base, then all you have to do is acidify the solution and you'll get it into solution. But what if your anion is not a strong base, like silver chloride? Chlorine is not, it's a very weak base. Why? Because this is a strong acid. This is a weak base. Okay, so you can't use that scenario for silver chloride. Won't work. If you acidify it, it'll make it less soluble. Okay, so if that's the case, right, if the anion is not sufficiently basic, then you need another scenario. Instead of attacking the anion, we attack the cation with complex ion. Okay? So those are your two possibilities for making a solid, an ionic solid, more soluble. Depends on the anion. The strong base, acidify. There's a weak base, complex ion. All right. Oh, got a video. So let me get the sound pumped up.
First, let's calculate the molar solubility of silver chloride in pure water, and then we're going to compare the solubility that we get in part A to the solubility that we're going to get in part B. And in part B, it's no longer pure water. We're going to have some ammonia present. So we take some solid silver chloride, so that's this over here, and we put it in some pure water, and some of the silver chloride is going to dissolve, but most of it's going to stay in the solid form. So silver chloride is only a slightly soluble compound. So there's my little pile of undissolved silver chloride. But some of it does dissolve, and so we get a saturated solution of silver chloride. So there are silver +1 cations in solution, and there are also chloride anions in solution, and we have our solubility equilibrium. To find the molar solubility of silver chloride, let's go ahead and write down our ice table. So our initial concentrations, our change, and finally our equilibrium concentrations. Before we put the silver chloride in, we didn't have any ions in solution. So the initial concentrations of our product are 0, right? We have 0 for the concentration of our ions. Some of the silver chloride that we put in dissolved. So we lost a certain concentration of our silver chloride, and we're going to call that X. So we're losing a certain concentration of our silver chloride. If we look at our mole ratios, for every 1 mole of silver chloride that dissolves, we get 1 mole of silver +1 cations in solution. So for losing X over here, we're gaining X. We're gaining X for the concentration of silver cations in solution. And since our mole ratios are still 1:1, if we dissolve 1 mole of silver chloride, we gain 1 mole of chloride anions. So over here we get a +X. So at equilibrium, our concentration of silver cations is X, and our concentration of chloride anions is X. So we write our equilibrium expression, and since this is a solubility equilibrium, we're going to write KSP, our solubility product constant, is equal to concentration of our product, so that's concentration of Ag plus, raised to the power of the coefficient, so raised to the first power, times the concentration of chloride anions, Cl-, raised to the power of the coefficient, to the first power. So we can plug in our solubility product constant at 25 degrees. It's 1.8 times 10 to the negative 10. So we put in here 1.8 times 10 to the negative 10. And this is equal to, this would be x times x. So this is equal to x squared. So we can get out the calculator and solve for x. So we have the square root of 1.8 times 10 to the negative 10. So we take the square root of that, and x is equal to 1.3 times 10 to the negative 5 if we round that. So x is equal to 1.3 times 10 to the negative 5 molar. So that's the concentration of, let's say, our silver +1 cations in solution. That's also the molar solubility of silver chloride, right? That's how much we can dissolve. So it's a very small molar solubility. So silver chloride is only a slightly soluble compound. Let's see what happens when we have ammonia present instead of pure water. So we have a 3 molar, right? We have some ammonia present now. What happens when ammonia is around silver cations? Right? We get this reaction. So silver cations plus 2 molecules of ammonia give us what's called a complex ion over here. And let's show what's happening. So if we have a silver +1 cation, right, we have 2 molecules of ammonia. So let me go ahead and draw in my 2 molecules of ammonia. And this is certainly not drawn to scale. So I'll draw one in on that side. I'll draw another one in on this side. Remember your definitions for Lewis acid, Lewis base, right? A Lewis base is an electron pair donor. And that's what's going to happen here. The nitrogen has a lone pair of electrons, and each ammonia molecule is going to donate a pair of electrons to our silver +1 cation. Right, so ammonia is donating as an electron pair donor, so this must be our Lewis base. And the silver +1 cation is accepting a pair of electrons, so this must be our Lewis acid. So the formation of a complex ion is a Lewis acid-base reaction. And notice the equilibrium constant for this, 1.6 times 10 to the 7th. Kf is called the formation constant. This is a very high value for the equilibrium constant, right? So the equilibrium lies to the right, and this is a stable complex ion. So any silver ions that are in solution, if you have ammonia present, ammonia is going to pick up that silver ion and essentially remove the silver ions from solution. So if we go back up here and think about our equilibrium, right, if we have ammonia present, we're going to be removing silver cations from solution. Right, so we're decreasing the concentration of silver cations. We're decreasing the concentration of one of our products. And Le Chatelier's principle says if we're decreasing the concentration of one of our products, our equilibrium is going to shift to the right to make more. Therefore, increasing the solubility of silver chloride. More is going to dissolve because the ammonia is present, because of the formation of our complex ion. So if we added some ammonia, right, if we added a solution of ammonia here, we could get our silver chloride to dissolve, right, because it's more soluble because of the formation of a complex ion. So let's say we add enough ammonia solution where we get our silver chloride to dissolve here. So that's the idea. Adding our ammonia, right, caused formation of a complex ion which increased the solubility of our silver chloride. So we would expect an increased solubility here of our slightly soluble ionic compound silver chloride. And next we're going to do the calculation. We're going to find the solubility of silver chloride in our 3 molar ammonia solution. Now we've looked at 2 reactions. We've looked at the solubility equilibrium for our slightly soluble compound, and we've also looked at the formation of our complex ion. Now let's add those 2 reactions together to get our net reaction for what's happening. Right? So we're going to add our 2 reactions together to get a net reaction for what happens when you put silver chloride in ammonia. All right, we have silver cations on our reactant side and on our product side, so we can take those out. And so for our reactants, for our net reaction, we have solid silver chloride plus ammonia. And for our product side, we would have our complex ion and our chloride anion. So we have our complex ion, and we also have chloride anions, so Cl-. So that's the net reaction, and if we added those two reactions together to get our net reaction, we have a new equilibrium constant, which I will call K. And if you add two reactions together to get your new equilibrium constant, you multiply the equilibrium constants of those two reactions. So K is equal to KSP times KF. So if you did that calculation, 1.8 times 10 to the negative 10 times 1.6 times 10 to the 7th, you'll get your new equilibrium constant. And I won't do it here just to save some time, but if you do that, you'll get 2.9 times 10 to the negative 3rd. So that's a 9, 2.9. All right, our goal is to find the molar solubility of silver chloride in our ammonia. So we set up our ice table, so our initial concentrations, our change, and then our equilibrium concentrations. And let's pretend like we're starting out with our solution of ammonia and we haven't added any silver chloride yet. So let's go back up here and let's see what our concentration was. Well, we started with a 3 molar solution of ammonia. So let me put that down here. So our initial concentration for ammonia is 3 molar. And if we haven't added any of our silver chloride, then we don't have any of our complex ions. So the concentration, the initial concentration of our complex ion is 0, and we also wouldn't have any of our chloride anion either, so that concentration would be 0 too. So now we add our silver chloride to our solution of ammonia, and some of our silver chloride is going to dissolve, and so we make that concentration X. So we're losing a certain concentration of silver chloride, so we write minus X. Next, we look at our mole ratios. So the mole ratio of solid silver chloride to ammonia is 1 to 2. So for every 1 mole of silver chloride that dissolves, right, we're also going to lose 2 moles of ammonia. So we write minus 2x here. For our products, if 1 mole of silver chloride dissolves, we make 1 mole of our complex ion. Right? So if we're losing X over here, we'd be gaining X over here for the concentration of our complex ion. And same thing for the chloride anion, because our coefficient is a 1. So we're going to gain X for the concentration of chloride anion. So at equilibrium, our concentration of ammonia is 3 minus 2x, our concentration of complex ion is X, and our concentration of chloride anion is also X. Next, we write our equilibrium expression. So K is equal to concentration of products over reactants. So I look at my complex ion over here, so concentration of our complex ion, and we raise the concentration to the power of the coefficient, so to the first power. This is times the concentration of our chloride anion, so times the concentration of chloride anion raised to the power of the coefficient, so raised to the first power. We also have some reactants here. So we leave silver chloride out because that's a solid, right? But we have ammonia. So this is all over the concentration of our reactant. So this is over the concentration of ammonia. And notice our coefficient is a 2. So we need to have a 2 here. Next, we plug in our equilibrium concentrations. So our equilibrium concentration of ammonia is 3 minus 2x, our equilibrium concentration of complex ion is x, and our equilibrium concentration of chloride anion is x. So on the right side, we would have x to the first power times x to the, let me take that out, times x to the first power. Right, all over 3 minus 2x to the second power, so squared. And then we can plug in our equilibrium constant k, which is 2.9 times 10 to the negative 3rd. So 2.9 times 10 to the negative 3 is equal to, on the right side, we would have x squared. So let me write this out. We would have x squared over 3 minus 2x squared is equal to 2.9 times 10 to the negative 3rd. And so what we could do here, these are both x squared, right? These are both x squared, so we could just say that this is all squared on the right side. And then we could take the square root of both sides, right? So take the square root of 2.9 times 10 to the negative third, and take the square root of what's on the right. So the square root of what's on the right would be x over 3 minus 2x. And let's take out the calculator to do the other one. So square root of 2.9 times 10 to the negative third is equal to, let's round that to 0.054. So it just makes it easier here to round that. So 0.054. Our goal is to solve for x. Our goal is to solve for the molar solubility. So we can multiply both sides by 3 minus 2x. So when we do that, right, we would have this. So we need to multiply 0.054 by 3, and if you round that, you're going to get about 0.16, and 0.054 times 2 is approximately 0.11. So we have 0.16 minus 0.11x is equal to x. So we have 0.16 is equal to, we put both x's on one side. This is 1x, and this is 0.11x. So 1x plus 0.11x is 1.11x. And so now we need to solve for x. Right? So we've done our math here. So we have 0.16. We need to divide that by 1.11, and that is equal to 0.14. So x is equal to 0.14, which is only approximate because of all the rounding that we've done. So this is concentration, right? So this is our molar solubility. If we go back up here, x equal to 0.14 molar, right? So that's our concentration of complex ion in solution at equilibrium. That's our molar solubility of silver chloride, right? So it's 0.14 molar. Let's go way back up to the beginning and compare the molar solubilities. Right, so in pure water, the molar solubility of silver chloride is 1.3 times 10 to the negative 5 molar, which isn't very soluble at all. But now we have ammonia present. We've increased the solubility, and we just calculated the molar solubility is 0.14 molar. And obviously 0.14 molar is a lot larger than 1.3 times 10 to the negative 5. So the formation of a complex ion increased the solubility of our slightly soluble compound, silver chloride.
All right. The reason I let that all play out is because next week, I believe, our lab, and let me verify that. Yeah, next week our lab is on the formation of that complex ion. Let's see. I didn't give you a copy of that yet, did I? Okay. We're going to, in the lab, we're going to do an experiment that will allow us to calculate the formation constant for the complex ion, silver with its two ammonia's ligands. And I'll give you a chance, both of you a chance to chew on that one and set up your lab notebook. It's fairly simple. Let me be sure this is the right copy. Oh, no, wait a minute. Yeah, okay. Actually, what we're going to do is we're only going to do the first experiment. On page 2, you got that chart, and it's got 2 experiments in there. The first one starts off with 5 milliliters of 0.1 molar silver nitrate and 5 milliliters of 1 molar ammonia. And then the second one has the same amount of silver nitrate, but twice as much ammonia. I found that that second one doesn't cooperate very well. So we're just going to do the first one. So when you set up your lab notebook, you only need space for that first reaction. And we'll talk about next week, before we go in the lab, we'll work on this on the board and answer any questions you have on what's actually going on. The experiment itself is pretty fun. You have to do it in the dark because we need to use the Tyndall effect. Have I described the Tyndall effect? Okay. The Tyndall effect, when we here. The Tyndall effect is the way you tell the difference between a solution and a suspended solid, or a colloid, we call it. So if we have a beaker and you have a solution in here, and it is a true solution, then when you take your flashlight and you shine a beam through it, you can see it, see the beam come out the other side if your eyes are over here. But if your eyes are over here, you can't see anything, right? You can't see where the beam's going in that solution. Right? But if it's a suspended solid, like we run our experiment, we precipitate silver chloride in solution. It's very, very, very finely divided. It's difficult to see with the naked eye. But if you shine a light through a colloid like that, or suspended solid, you'll be able to see the beam of light reflected off those little particles. So that's what we use to find the endpoint for our titration. We're going to titrate against sodium chloride that forms. We're going to titrate actually the complex ion with hydrochloric acid. And when we reach the point where we've got enough chloride in there to start forming silver chloride, then that's our endpoint. We're going to use that information to determine the complex ion, the KF. We're going to calculate the KF for that reaction, and whatever it happens to be. It should be very close to the one that Saul Kahn showed us just a minute ago. Okay. And that whole description is right there in the method, but we're going to talk about it anyway because it might need some explaining, further explaining. Okay. What are the relevant species in the dissolution of silver chloride in excess ammonia? Right. So here we have the solubility constant for silver chloride, and here we have the formation constant for ammonia, but that's in 2 steps. Okay, here, the second step, there we go. Right. So in that video, we saw the formation constant for this one was a combination of these two. And the equilibrium is going to lie far to the right for this one. And in combination, it's also going to drive the reaction to the right for this one. So when we put all 3 of those reactions together, this is what we get. And notice that the silver ions cancel out because they're on the same side. One on this side, one on that side. So there's no silver ions that are part of this calculation. And there's your decay equilibrium constant for this composite reaction. Okay. So if we do this calculation, and all we have to know is what's the concentration of the complex ion, chloride ions, and ammonia in solution. And what we note from this is that this K value is the reason that we have such high ammonia concentrations. If this were very, very small, then these would also be very small. because that is 10 to the minus 3. So since this is a constant, then if we increase this, then this has to increase also. Right? It's just the nature of a quotient. Oh, okay. So if our ammonia is 10 molar rather than 3 molar, right? If it's 10 molar, then we do the similar concentration. And it takes 2 of these. I think Saul Kahn had this one also stuck out here, but that was just to impress upon us the fact that it's all based upon the solubility of this. That's what X means. X is the solubility of silver chloride. But the equilibrium reaction doesn't involve that. The equilibrium constant does not involve the solid. The reaction obviously involves the solid, otherwise we wouldn't have it. So if we have 10 molar ammonia and we're starting off with nothing here, then for every one of these, which is tied to this silver, 1-to-1 silver, so X is the solubility of silver chloride. We get 1X here, we get 1X there, but we lose 2 ammonias. So this is the equilibrium situation. Then we just set that equal to the equilibrium constant and solve for X on the next slide. Here we go. Okay. And X is 0.47 molar. So in the video, we had 3 molar ammonia and the solubility was 0.14 molar. We increased the concentration of ammonia to 10 molar, went from 3 to 10 molar ammonia. And now the solubility of silver is 0.47 molar. So we increased it by 3.5, 3.7, something like that. Okay, so how much ammonia is left in solution? Right. This is what we started with, 10 molar, but we had to subtract 2 X's, correct? Based on our ice table. And our X has to be 0.47, so we have 9 molar ammonia left in solution. We've still got a lot. In fact, you put your nose over it, you can probably smell it. Okay. Oh, the end. That's it for the slide set. Now, the real, as is usually the case, the real understanding comes from working these problems. Work out those equilibrium problems. And then that's where you develop your chemistry skills.